Hello, mathematical brains. In school, in high school, in college, everyone talks about the real numbers and they put a weird R on them. Okay, we are all familiar with them, but does anyone know how to define them? Moreover, can they really be defined? Let's take a look at the real numbers, and I already warn you that it will not be simple. Who said fear? We started. Hello friends, this video is sponsored by the Polytechnic University of Valencia. Let's get into the basics of mathematics a little, and that always turns out to be weird, but it is necessary. Friends, we cannot stay without understanding things. We are going to start with very simple things and we will get to quite complicated ones. Stop when you feel like your head is going to explode, okay? As a precaution. Above all, we have the numbers to count, the 1, the 2, the 3, and so infinite numbers. The first time we heard about the infinity thing, we freaked out a lot and told mom that we love her infinitely and 1,000 times, and things like that. Then someone tells us that, in addition to those counting numbers, which it turns out are called natural, there are equal but negative ones, and all of them together, including 0, are called whole numbers. They can be added, subtracted, multiplied without difficulties, a feast. Later it seems that someone came up with the idea of drawing a line, put an integer above it and call it a numerator. Put another one under it, call it a denominator, and let all that be a number that we call a fraction, and that is equivalent to the result of dividing the numerator by the denominator. And that's almost never is an integer. And those numbers are called rational. Very crazy everything. And that's where the mess starts. Rational numbers are a mess. To begin with, some that look different, it turns out that they are the same, like 3/4 and 6/8. On top of that is all that decimals, periodic decimals and such. Of course, rationals are also infinite, of course, just like natural ones or integers. And on top of these numbers you can also add, multiply, subtract and divide without problems. No real problems. That they ask it to people who are learning now to add fractions, with that of the least common multiple. It seems that these rationals are good for everything, right? We can rest now. We have numbers that are used for things as big as we want and as small as we want, and they are more or less simple. In fact, for algebraists, rationals are much simpler than integers, for reasons that I may explain another day when you are ready, really ready. Well, the fact is that one day the math teacher comes very happy saying that there are numbers that cannot be imposed as fractions, that there are numbers that are not rational, they are called irrational. But what is this mess? Peace is over. If the teacher has one fine day, he or she sets out to prove that, for example, the square root of 2 is not rational. Sit down if you are standing. It turns out that the irrational numbers are not a few, they are a lot, there are infinitely many of them. In fact, there are many more than rational, more infinite than infinite. There are very famous ones, like pi or like e, but it is also that each of those monsters has infinite decimal places that do not follow any pattern. You know, how it happens to pi or e. In this they are nothing special. It's true. Anyway, by that time we are already in high school, and the teacher tells you that we put the irrationals and the rationals all together in a set, and we call that set the real numbers, and we put a rare r in it. Let's see, I know that teachers do this so that no one cries, no one's eyes bleed or feel like calling their mom in class, but that definition of real numbers leaves you a little dissatisfied. Let's try to define them in conditions. Let's get to work. We say that the real numbers are a set that verifies a series of properties that make them a complete ordered body, and that makes the reals the basis of the calculation of mathematical analysis. Calm down, although this sounds very, very, very strange, however it is not so much. Let's try to explain it little by little. To begin with, we start from a set of elements. Those are going to be the real numbers, and a couple of operations between them, addition and multiplication, subtraction and division, come as a gift with it. The first thing that this set has to fulfill with those operations is that it has to be a body. What does that mean? Well, basically that we can add, multiply, subtract or divide any pair of elements and the result will still be within the set. There also has to be a neutral element, identity, etc., but I don't want to make it long. Look, for example, integers do not form a body, because if I divide 3 by 2, the result is not an integer. Those aren't worth it. The rationals yes, because take the 2 that I take, if I divide or add, or multiply, or whatever. The result is another rational. Being a body comes first, but it's not enough. The second thing is that it has to be a totally ordered set, that is, that given 2 elements they are either equal, or one is greater than the other, or vice versa. In addition, that order has to be compatible with the sum and the product. Well, that's easy, that's what rationals do too, even integers do it, but it's not enough. There is one more property that must be fulfilled. Pay attention now that here comes the key and it is the difficult part. It is called the property of the minimum upper bound. The name is scary, but it's not a big deal. What he means is that, if I take any subset of elements that is bounded above, that is, there is some number larger than all of that set. That is called an upper bound, so there is a minimum upper bound. That is, there is a number larger than all of that subset, let it be the smallest that has that property. And that has to always happen for every bounded set. And it happens that the rationals do not comply with that. I'll give you an example. I'm already seeing people drooling in the fetal position. Let's see, let's take the set of all rationals p, such that p squared is less than 2. The 1 belongs to that set. 1 squared is less than 2. A half 2, but for example, 3 half no longer, because 3 half squared is 9 quarters, and that's greater than 2. 3 means is greater than any element of that set. It's a higher level. The subset is bounded. However, there is no minimum upper bound for that set. It's a bit long to demonstrate now, but it's simple. Okay, the rationals are a body and they are ordered, but they don't have the axiom of the minimum upper bound. There has to be something beyond the rationals. If we manage to build an ordered body and with that weird axiom, we have the real ones. And you can, friends. In fact, there are several equivalent constructions, each with its advantages and disadvantages. One was made by the great Cantor using some stuff called Cauchy successions. Another very good one was made by Dedekind with an idea called Dedekind cuts. If you dare, I will tell you about it and so you can doubt that you know what Dedekind's cuts are. Rest assured that I will give you a simplified version. If you have come this far, it is because you are brave. Dedekind defined a cut. Let's call it R, like any set of the rationals that satisfies that R is not empty. R is not all rationals. For each number in the set R, all those that are smaller than that number are also in the set R. And R has no maximum element. Well, Dedekind defined the reals as the set of all the cuts R. Remember that each cut is a set. Well, the guy defined how to add those sets, how to multiply them, how to order them, and everything works as we want it. They even comply with the minimum upper limit. That is, the cuts form a complete ordered body. It is quite amazing that every integer, every rational number and every irrational number corresponds with a different cut, and they add up, multiply. Just like we're used to. For example, the slice formed by all rationals less than 3 means corresponds to the number 3 means, which is a rational, and the slice formed by all rational numbers that are either less than 0, or squared are less than 2, corresponds to the irrational square root of 2. And so everyone. Dedekind was a genius. Thanks to him the reals are well defined, and if you want to see the teacher sweat, tell him one day in class to define the reals. See you in the next video.